All right, so I've added some new videos to lecture videos. Let's see, chapter 9, it was given to you guys before and we kind of covered it. It was somewhere in here, so I moved it now to have the correct order. So that's why you see it's lecture 12, because it was right here between chapter 5. So if you look at your textbook, Centroid, which is topic of chapter 9, is covered at the end of chapter 4. Okay, and then again repeated as chapter 9. So that's why this lecture was presented to you. So it's pretty much, I could have called it end of chapter 4 and have it again here, but just have one lecture. So now we're going to get more examples of centroid. We didn't do much other than a rectangular section and a triangular section. But we're now going to do any type of area or any type of curve. You're going to learn how to do it. The other video that I've added is chapter 10, which we're going to start Monday. And last example or last portion of examples of chapter 8 that you guys can do. Okay, so please watch this one for your next exam, and then watch this one for Monday. Okay, so we're gonna get into this, but before starting examples of chapter 9 and centroid, I want to do one thing that I assigned to do on as a self-reading, friction on belts. So we're going to do this one. A rope having a weight per unit length of 0.4 pound per foot is wound 2.5 times around the horizontal rod, knowing that the coefficient of static friction between the rope and the rod is this much. Find the minimum length X of the rope that should be left hanging if a 100-pound load is to be supported. So this rope has weight. Okay, the weight of this rope is 0.4 pounds per every foot of this rope. So for example, weight of this section of it is 10 feet multiplied by 0.4 pound per feet, and it's going to be 4 pounds. Okay, so weight of this section of it is 4 pounds. There is this section that we don't know. Weight of this section is 0.4x pound, whatever that length is, and it's wound 2.5 times. We have also the coefficient of static friction. All right, the equation that we use for friction on belts is an equation like this, and this equation is always given. All right, so you don't have to memorize it, you don't have to derive it, but you have to understand what is T2, what is T1, and what is beta. Okay, so the first thing I want to do is I want to take a very short quick quiz here. All I want you guys to do doesn't really need any calculation or anything. Find beta. What is beta? The value of beta in this problem. Okay, so if you're in your classroom, all you have to do is just write the value of beta. That's it. If you're in the classroom, Colton will go around and do it. If you are online, I added a link on Blackboard. All you have to do is click on it, okay, and write a submission. Just write the value. That's it. Okay, that's all you have to do and submit. Okay, so I'll give you about 3 minutes, because again, it doesn't need any calculation or anything like that. You either know it or you don't know it. The question is, what is beta? Okay, 3 minutes. How many people do we have in the classroom, Colton?
I only have 5 in the classroom today.
Okay, so if you just go around and just get their number, their name and value of beta, that would be great. All right, enough thinking. So everyone should be heading to Blackboard assignment section, click on quiz 8 and enter your value. Okay. I'll wait another minute and then I close the link. All right, Colton, did you get the numbers? I see you walking around, but
Yeah.
okay. All right. So last 30 seconds and then I'm gonna close the link. All right. Okay, so now let's look at the solution and figure out how to solve it. First of all, what is theta? What is beta? What is it? We know mu is coefficient of static friction, right? So this is coefficient of friction. Well, what is beta?
Angle of built to surface contact.
So it's angle of, exactly, you said it completely, and all of it. So angle of belt to surface. So it is how much this rope is contacting the surface of the pulley, whatever, in this case, a cylinder. So if this rope is going around 2.5 times, 1, 2.5, then what is beta?
2.5.
2.5 what? Is that an angle?
Radian.
2.5 radian. Is that correct?
It'd be 2.5 times 2 pi.
So it's 2.5 times 2 pi because a full rotation is 2 pi. The angle, right? This angle is 2 pi. So first of all, this beta needs to be in radian. Okay. If you forgot radian versus degree, so every 360. Okay, doesn't stay there. 360 degrees is 2 pi radian. So 1 degree, and then you can find the radian value for it. So 2.5 times 2 pi. 2 pi, that's our beta. Okay, we have everything else. We have mu. E is just a constant number. The only thing we got to figure out is let me see. Oh, this is a word. That's why it doesn't. There we go. So the only thing left is figure out what is T2 and what is T1. So what is T1? What is T2? You know, let me draw a kind of a free body diagram for you. It's not an exact free body diagram, but kind of. This is a cylinder. Okay. I'm gonna put a force going down. I'm just gonna call it T for now. And then T2, and then I have friction all along the surface. So I'm just gonna put it like this. So can you guys tell me which one is T2, which one is T1, which one is T2, which one is T1? Which one is bigger, which one is smaller based on this equation? Come on.
T2 is bigger.
T2 is bigger? Okay. On which side is that one? Is that side 1 or side 2?
It's the side that's going opposite of the friction.
It's the side that's going opposite of friction because look, this is an equilibrium, right? So this two sides should be equal. Friction plus T1 should be equal to the other one, all right? So T2 is bigger than T1 because T2 is that one plus friction. So I think we can figure this out now. This one, T2, is 100 pounds plus 10 foot, 0.4 pound per foot. This is going to be 104. T1 is x multiplied by 0.4. So I think I'm ready to just insert it in this equation. So it's going to be 104 pounds, 0.4x e to the power of 0.3 multiplied by 2 pi. The only unknown here is x, and you can find x equal 2.3 feet.
Is it
Okay.
supposed to be? Is it supposed to be 5 pi?
5 pi, yes. Sorry, you're correct. 2.5 times 5. So beta, I'm going to write it here. Yes, you're correct. So all of there are, I think, 1 or 2 examples in my lecture videos that you can do with belts. But again, in all of those problems, the only thing you have to figure out is beta. Once you have the beta, the rest is really easy, okay? Pretty much you have everything else. So in problems that we have done in the class, so now here's a good exercise for you. So first of all, question about this before I move on. If you didn't read the book or my lecture video about frictional belts, please do so. It's just 1 page and it derives, or 1.5 page. It derives the equation, it explains everything, it tells you where this equation come from, why beta is beta and everything, okay? But I'm not gonna derive the equation in the class. we never do, we just give this equation and say, hey, this is equation for friction on belts. But if you want to know behind it and what beyond it and what happens, please read the book on this. Okay, so here's a good example. The problem that we did, if you remember this one, where did it go? Yeah, this problem. So this is a very good one. So repeat this problem that I did in class. And remember the free body diagram, there was a T here, and then for B also there was a T. These two are equal, right? Because this was frictionless. So now just add another mu of whatever, 0.2. Now it's not frictionless anymore. So now these are not equal anymore. All right. So one of them called T, one of them is called T prime. You have to use an additional equation, the equation for friction on belt, to figure these two out. All right. That's the only change that happens. Before, T was equal between the two. Now you have an extra equation, the equation of T2 equal T1 E mu beta. That's the relation between them. Before, these were equal without friction. Okay, if friction is 0, so this is going to be e to the power of 0, so T2 equals T1. But with friction, you have to multiply that too. So this is an excellent example that you can modify and do it on your own. There is this one that I solved this one on my lecture videos. Okay. If we have time, we'll get back to chapter 8, do a little bit more friction. But right now, I just want to move on a little bit. Okay. Any questions about friction stuff before we temporarily say goodbye to chapter 8? Okay. So let's get to chapter 9 and Centroid. Okay. All right, let me open the whiteboard here. All right, so the problem says find a centroid first without this square cut out of it. Centroid of this area. Okay. So let's see who remembers what is the equation for centroid. Does anybody remember? First of all, what is centroid? Let's just start with more basic stuff. What is centroid?
Center of mass is
Nope,
what they're all saying.
it's not.
Center of area.
Center of area, it has nothing to do with mass. I don't see any mass here. All right. What is what is center of mass called?
Center of gravity.
Ooh, nope. Didn't you guys do an exercise on difference between weight and mass? So what's center of mass called? Center of mass is called center of mass. Okay, center of weight is called center of gravity. You're right. Okay, for a body particle area which is homogeneous, means the density, the rho, is same all over. all of these could be on the same point, but they could be different. All right, they all can happen at the same point, but they could very well all of them be different. All right, but center of mass and gravity, no, but centroid and center of mass, center of volume, all of those stuff that I covered in lectures, center of length, all of those could be different depending on the part and depending on the body that we're doing. But centroid is not center of mass. And I remember when I asked this before, people also still say center of mass. So center of area, okay? Where did we use centroid? Why did we cover it already and used it? Where did we use it?
Distributed loads.
Distributed load, right? So I had a beam. There was a load like this on it, right? We said, hey, the equivalent force is located at centroid of this area. Show it with the X bar. So we know for this is 2/3. This is 1/3 here. For a rectangular area, this is located at center, right? But what is the general equation for it? Who remembers the general equation for an area like this? Who remembers centroid? Got to go back to your chapter 4 notes if you have your notes with you. We covered this in chapter 4. Anybody? Anybody remember it from math classes? Because this is not a statics. This is a math issue. Okay.
Would
Anybody
just be
remember?
the integral with respect to x over the average value of the area, or like over the area.
Okay, so kind of, yes. It is area integral of x tilde, the area, over the area. Okay. So now let's figure out terms of in this integral. So I have to figure out two things. I have to figure out x tilde. I have to figure out dA. And if I do that, then I can solve this integral, right? So what is x tilde? Let me ask you this first. What is dA? Let's get that figured out. Again, these are math questions, all right? Has nothing to do with statics. What is dA?
Derivative in terms of A.
Area in terms of A. What does that mean?
Derivative in terms of the area.
Oh, it's not derivative. This is not a derivative. What is dA? Anybody? So if I have this graph here, right, the part A says without that block cut out. All right, this is my y-axis. This is my x-axis. What is dA? So let's see. Someone said derivative of area. What does that mean for this area? I don't have an area, right? I want to find area.
Function with respect to x.
So dA is function with respect to x. What does that even mean? Function respect to x.
Does it mean you're integrating x with respect to the area?
No, forget about x. What is dA?
The integral of the function from point A to point B.
So dA is integral of function, which I don't know what function it is. Maybe they mean this, from 1 to 2. Is that what dA is?
Isn't it just like the area of the closed space?
So why do I not just call it area? Who remembers the integral?
Isn't
What-
dA just delta x?
When you do an integral of something like from a function, that's how you can find, I guess, the area underneath a curve. So
Yeah, but I want to know, what is dA? I understand integral and stuff. Someone said delta x. So let me ask you a more basic questions. What does integral mean?
It's the area under your curve.
No,
Your
in
function.
general. What is integral? You're correct. The answer of the integral is the area under the curve. But what is the meaning of integral? What do we do when we integral or integrate a function or do an integral? What do we do?
you're summing up a bunch of values.
Okay, we're getting somewhere. So we are summing bunch of values. This integral means addition, right? So what is the difference between sum then? You know, someone said summing some values. We have summation of f's, right? So why don't we, instead of integral, say summation of x? Why don't we use integral? What's the difference between these two?
On the integral, you're summing an infinite amount of areas.
Okay. And you said a word that made me kind of happy. So infinite number of areas, right? Again, I didn't want to focus on area, anything, but you're correct. So the difference is if you use sum of f's, right? We use this a lot in this course. You have finite number of f, meaning you have 2, you have 3, you have 10, you have 1,000. You can count them, right? But with this one, you don't know how many. They're infinite number of areas.
So in other
Okay.
words, you can count a summation as discrete, and then an integral is, I guess,
Exactly.
continuous.
Yes. Exactly. So this is a continuous addition. You start from this point, and that's what it means, right? 1 to 2. You start from point 1, you end up to point 2. These are not number 1 to number 2. I've seen a student integral. It means point 1 to point 2, whatever that value is. Okay. So now you know integral. So now let's go back, figure out what is dA again. Now, can you tell me what is dA when I say integral of dA? So I'm integrating dA. What does integral mean? Addition of infinite number of what? So I'm adding what?
All the area?
I'm adding
All
infinite.
rectangles until it gets to infinity.
Okay, exactly. So I'm adding infinite number of little areas, like sliver of an area, a very thin little tiny area, right? So, and that's what integration means. Integration is an approximation, right? We say, hey, you know what? I can divide this curve into little rectangles, and then I can assume if I just add all of those little rectangles together, how many, doesn't matter, add them together, I can get the area. So these DAs are these little tiny slivers of area. They are a differential amount of area. Okay. That's different than delta A. That's different than delta X. It has nothing to do with X. This is just a little tiny sliver of area. So let me draw it better now. And this is a required, all right? So instead of free body diagram, now we're gonna draw this. So I'm gonna draw a little tiny thin area here, okay? This is my DA. I'm gonna get back to how to calculate it, but for now, that's DA. So now let's get back to X tilde. What is X tilde? I need two things to calculate the centroid of this area. X tilde and area. So I figured out DA. It's a differential amount of area, or it's a tiny element of area. They're all the same. What is X tilde? So this I figured. What is X tilde? Seriously, no one remembers anything from chapter 4?
Isn't it just the center of your rectangle from the y-axis?
So it is the centroid of that little tiny DA. Okay, and you're correct. When it's X tilde is from y-axis.
And y tilde is from x-axis.
Y tilde is centroid of DA from y-axis, okay? So if this is really tiny, really tiny, so this is my X tilde, okay? So it is important to understand these two, because really the equation for centroid is very simple. X tilde DA over DA, and that's it. But you have to understand what DA is, what X tilde is, all right? So this is just what they mean. Now let's look at solving the integral. So I need some values, some equations now. So what is this DA now in terms of X and Y? Now you can think about X, now you can think of Y.
Isn't it just y dx?
It's Y dx, exactly. So it's a rectangle, right? So it's this length, which is Y, multiplied by this little tiny, very thin length, because it's on x-axis, it's a differential amount of x, so it's dx. So it is y dx. So dA in this case is y dx. What is X tilde in this case? Which axis X tilde is moving on?
On the x-axis.
So it's from the x-axis. So wherever it is, this value, same as value of x. So it's x. All right. See, that's it. Now I'm ready to calculate x bar. It's x tilde, which is x, dA, which is y dx, over integral of dA, which is y dx. I need two bounds for my integral. This one is 0. What is this one? So it moves from 0 to what?
It's other root.
Which is what? So integral is addition, right? So addition all dAs from point 1 to point 2. That's the meaning of the bounds of integral, right? So it starts from 0 all the way to what?
12.
12. Okay, it's not given, but that's just root of this equation. All right, can I do this integral now or not yet?
No, you'd have to solve for, well, no, never mind.
So I can. Should we do another quiz, solving integral?
You would want to substitute the equation in for y, so then you just have x's.
Okay, exactly. So when your variable is dx, everything here should be just based on x. All right. One other thing that it's good help to tell you guys is that when your variable is x, this bounds of integral are also same as x. They move on x-axis. We don't care about y-axis. They start from 0, they go to 12. Okay. So how can I change this y and have everything based on x? My dA is x, y dx. How can I change this and make it all based on x?
You're given that y is equal to negative 1/6 x squared plus 2x.
Exactly, y is given. So minus 1.6 x2 plus 2x dx. That's it. So let's substitute it. 0 to 12 minus 1 over 6 x2 plus 2x dx. 0 to 12 6 x2 plus 2x dx. Okay. Oh, there's an x here. Sorry. Okay, so if you do the integral, you're going to get 288, 48. Okay, what are the units? What is unit of this 288 and what is unit of 48? This problem, all the units here are meters, 6 meters, 2 meters. So this is meters, this is meters. So what is the unit of that 288? What is unit of area?
Meters squared.
Okay, so at least we know this one is meters squared, right? This is area. Okay, what about top one then? What unit should you get? What should you get for X bar centroid?
Meters.
You should get meters. So what unit do you think the top should be?
Meters.
Meters cubed.
Also, so here's an X, right? So this is meters, this is dA, so this is meters squared, this is meters squared. So the units are meter cubed over meter squared, which is meters. All right. So the units also make sure to check them. Make sure they check out. All right, so this was kind of a, you guys are a little bit rusty on the math and integration and all of that. So you got to do a little bit, again, this chapter is purely math, as you can see, is integration and stuff. It has very little to do with the statics. You know, I try to relate it to statics. You're going to see in the next example that I'm going to do, but it's mostly math skills and integration. Questions? So I totally ignored this for now. Okay. As if this was just full. Any questions? Okay, so let's do the second part, which says, I don't want to clear it because I might lose the figure. The second part says, now the area is gone. Now, what is the center of area? First of all, the centroid was 6 meters, by the way, right? It was kind of in the center. Part A, the X bar was 6 meters. Part B, now this is cut out. Do you think the X bar for part B is going to be more than 6 or less than 6? Just if you want to just guess.
Less than.
Why?
Because it's cutting out something that's farther away.
So center of area, right? So the center of area was kind of here before on this line. This is what we found. We found the distance of this line to be 6. Now the second half of it, parts of it is cut out. So I have more area on this side than I have more area on this side. So the center is going to be shifted a little bit this way. Okay. So again, so I have an equal amount of area on both sides of that. How much? I don't know. Now I got to do another integration and all of that. But I'm going to do something much simpler. This is what we call the composite shape. Okay, so let me do it here. A composite area means it made up of 2 or more. Okay, so this shape, this is what I had, right? A full area, and I deducted a little area from it. Okay, so this little square was deducted from this area. As a result, I'm getting the shape that you guys are seeing, right? So all I have to do is do an X bar equal integration for this one minus integration for that one to get this. Okay. So this is how I do composite area. If there was something else added to it or deducted from it, same. You just keep going. Add another area, deduct another area, and so on. Okay. So I already found these two. All I have to do is do these one. So first of all, what is dA2? Integral of dA2. Can someone tell me just by looking at a figure?
It would be 4.
It would be 4 because this integral means area 1, this area, which I found it to be 48. Area 2 is just area of this one, which is a 2 by 2, which is a 4 meters square. So I don't need to integrate this one. Okay. What about this part? Can you guys do this part also without integration? So what this means is pretty much x tilde multiplied by area. Can you guys tell me what is x tilde here? And what is
Would be
area?
7. As
It would
x
be
tilde is 7.
it would be centroid of this area that I'm trying to find, the distance between this one and y-axis, which is 6 plus 1. And I already have the area. So this whole thing is going to be 288 minus this one was 7 by area, which was 4. A1 was 48. Area 2 was 4 meters. So this will result in 5.91 meters for my new centroid of this shape. Okay. So this is, again, what is called a composite area. You just add them together or deduct them together. If I want to add another shape here to this area, add, I don't know, a rectangle here. All you have to do is add that into your equation, okay? Just hypothetically. You have to add this area here. So your integral is going to be plus x tilde 3, the area 3, and so on. Okay, or area 3. So we're going to do more examples on composite areas and stuff like that. All right. Questions? Okay, so rest of the semester is just going to be spent on centroids and second moment of inertia, which we start on Monday. And the reason that I want to start that one right after this, because a lot of problems ask you to do both of them. Gives you an area, it says find second moment of inertia, find centroid for it. So we need to know chapter 10, and then we can do all of these problems. So pretty much you're going to see the same problem. It tells you find x bar and find I, and that's the lecture I put for chapter 10 that we're going to do Monday. So, okay. For your next exam on Wednesday, it is just going to be on friction, only on friction. This is not part of your exam for next Wednesday. These are going to be part of your final exam. All right. If you guys have any questions, I'd be happy to answer. If not, have a good weekend, and I'll see you on Monday.
Is just a quick question. The finals are cumulative, I'm assuming, right?
Yes.
Okay.